Hey everyone, and welcome to this explainer. You know, if you've ever cracked open a smartphone, a television, or really any piece of modern tech, you've undoubtedly seen them. I'm talking about those tiny, colorful, striped little components scattered all over the circuit board. They're called resistors, and honestly, they act as the absolute heart of the electronics world. Today, we're going to completely demystify these fascinating little devices. We'll cover what they actually do inside a circuit, how to decode their secret colored stripes, and how to figure out exactly which one you need for your next project. Here is our roadmap for today. We are going to cover what are resistors, Ohm's law, types of resistors, reading color codes, and finally, power and connections. Let's get right into it.
Section 1. What are resistors, the valves of electronics?
Okay, let's actually dive in. At its core, a resistor is what we call a passive component. But what does that actually mean for the electricity zipping through your circuit? Well, to really grasp this, I want you to picture a huge water pipe. Imagine water is just rushing through this pipe at high speed, high volume. Now imagine we install a valve right in the middle of that pipe, and we partially close it. What happens? The flow of the water is instantly restricted, right? It's controlled. This is exactly what a resistor does in an electronic circuit. The flowing water is your electrical current. The pressure pushing that water, that's the voltage. And the restriction caused by the valve is your resistance. Without this electrical valve, sensitive components in your devices would literally be flooded with way too much electricity and destroyed in seconds. Let's frame this with a practical, real-world problem. Say you've got a fresh, beefy 9-volt battery, and you want to power a tiny little LED light that only needs 2 volts to shine. If you were to connect that 2-volt LED directly to that 9-volt battery, boom, no way around it, that LED will instantly pop from the excess pressure. So obviously we need a resistor to act as our protective valve. But how in the world do we know which specific resistor to use? Section 2, Ohm's law, the mathematics of resistance. This brings us perfectly to our mathematical toolkit. This is how we calculate exactly how much resistance we need to save our little LED. Resistance is measured in a standard unit called ohms, represented by the Greek letter omega. Just to give you a sense of scale here, 1,000 ohms is a kiloohm, and 1,000,000 ohms is a megaohm. Now, the way a resistor behaves is defined by Ohm's law, which states that voltage equals current multiplied by resistance. Or, keeping it simple, V equals I times R. Let's apply this formula to our exploding LED problem. It's like a puzzle. Step 1, we need to figure out exactly how much voltage the resistor needs to block or drop. We have a 9-volt battery and a 2-volt LED. Simple math. 9 minus 2 means we need to drop 7 volts. Step 2, we identify the current our LED needs, which is usually around 20 milliamps, or 0.02 amps. Step 3, we just rearrange Ohm's law to solve for resistance. So resistance equals voltage divided by current. That is 7 volts divided by 0.02 amps. Do that simple division and you get 350. That means to safely light up our LED using that 9-volt battery, we absolutely need to place a 350 ohm resistor into the circuit. And just like that, you've used fundamental theory to solve a very real, practical problem. Section 3, Types of Resistors. Finding the right flavor. Okay, so now that we've got the math down, we need to know what to actually look for when we open up a parts bin. Resistors come in a bunch of different shapes, sizes, and flavors. First up, we have fixed resistors. These are the ones where the value never changes. The most common is the carbon film resistor. You'll recognize it by its light brown body. Then you have metal film resistors, which are usually blue and are used when you need super precise accuracy. For circuits pumping out a lot of heat, you'll see wire-wound or cement resistors. Those are the big, chunky white ones. On the flip side, we have variable resistors, and you use these literally every day. Potentiometers are the volume dials on your radio. Trim pots are tiny adjustable presets hidden inside electronics, and linear controllers are those sliders you push up and down on an audio mixing board. Then we have the special ones. These are non-linear resistors that actually react to their environment. An LDR, or light-dependent resistor, changes its resistance based on light. This is exactly how automatic streetlights know when to turn on at dusk. Thermistors, they react to temperature. Varistors are incredibly cool. If a massive voltage spike happens, like a lightning strike, a varistor's resistance instantly drops, safely rerouting that dangerous current right away from your sensitive components. It's basically a bodyguard for your circuit. Finally, we have SMDs, which are microscopic surface mount resistors found inside ultra-compact stuff like your smartphone. Section 4, Reading Color Codes, Decoding the Secret Language. Now, unless you're working with those tiny microscopic SMDs, most fixed resistors don't actually have numbers printed on them. Instead, they use a series of colored bands. I know, at first glance, it looks like complete gibberish, but I promise you, decoding this secret language is surprisingly easy. It relies on a universal color code that maps perfectly to a number from 0 to 9. From black at 0, working up through the rainbow to white at 9, you just match the color to its number. For a standard 4-band resistor, here's how the logic flows. The first band gives you your first digit, the second band gives you your second digit, the third band is your multiplier, which is just a fancy way of saying how many zeros you add to the end of those first two digits. And finally, the fourth band tells you the tolerance, meaning how accurate the manufacturing is. A gold band means it's accurate within 5%, and a silver band means 10%. Let's actually decode one together right now. Imagine you're holding a resistor with the bands red, red, yellow, and gold. Okay, first band is red. Check the chart, that's the number 2. Second band is also red, so another 2. The third band is yellow, which is our multiplier, meaning we add 4 zeros. Put that all together, 2, 2, and 4 zeros gives us 220,000 ohms or 220 kiloohms. That gold band at the end just confirms it has a 5% tolerance. See? It's just a fun visual puzzle. And hey, if you ever forget the colors, you can always just grab a multimeter to check it. Section 5. Power and connections. Building complex circuits. We are in the home stretch now. Figuring out the ohms you need is fantastic, but choosing the right resistor involves just a tiny bit more. We also have to consider physical power. Because a resistor acts like a valve blocking current, it naturally generates heat. The amount of heat it can safely handle without, catching fire, is measured in watts. For standard small electronics projects, quarter-watt or half-watt resistors are totally fine. But if you're dealing with high currents, you absolutely must step up to those larger 2-watt, 5-watt, or 10-watt ceramic resistors to prevent your circuit from overheating. And finally, what happens if you do all this Ohm's law math, but you search your desk and you just don't have the specific resistor you need? Well, you can combine them. If you wire resistors in a series, meaning end-to-end in a single line, their resistance values simply add up together. R1 plus R2. But if you wire them in parallel, meaning side by side where their ends connect, the total resistance actually goes down. In fact, if you put two identical resistors in parallel, their total resistance is cut exactly in half. This gives you incredible flexibility when you're building out a board. And there you have it. You now know how to identify, calculate, decode, and safely connect the foundational building blocks of all modern electronics. Resistors might technically be passive, but they dictate the flow of energy that makes everything from automatic streetlights to your laptop function safely. So my question to you is, now that you understand this secret language, what complex circuit are you going to design and build next? Thank you so much for joining me in this explainer. Keep learning, keep experimenting, and I'll catch you in the next one.